All right, let's get started. So we just have one last slide on the last unit, Unit 3, which is actually just sort of an introduction to the next unit. So just to sort of recap what we were doing, we were looking at model order selection. In model order selection, we are choosing among a set of models that range in complexity from simple, low complexity models to complicated, high complexity models. So as an example, we would have maybe like, are we going to use the first feature? Are we going to use the first two features? Are we going to use the first three features, and so on? And that especially made sense in polynomial regression, where this was like x squared, x cubed, and so on. But more generally, you could step back and say, well, wait a minute, is that really what we want to do? Or do we actually want to choose a particular subset of features? So maybe, for example, I want beta 0, beta 1, and beta 3, but I want to get rid of this one. Or maybe I want beta 0, beta 2, and beta 3, but I want to get rid of this one, and so on. So that problem, instead of model order selection, is called feature selection. We're actually just choosing which subset of features is going to work best to fit our data. So do you guys see the sort of, what's the main challenge to this problem that is a lot harder than this problem? Does anybody see what the challenge is going to be?
You'd have combinations of features?
Yeah. How many different subsets do we have to choose from if we have D total features? How many different subsets? Any ideas?
D factorial?
Not quite.
2 to the D plus 1, or 2 to the D.
2 to the D, exactly. The way to think about it is, imagine for every feature you have a binary variable 0 or 1 that selects whether you're going to use it or not. And now you have all these binary vectors of all the different ways you could use or not each feature. So you're going to have a binary vector of length D, so there's 2 to the power D possibilities. So, so that's the main problem. We're going from something that has a linear complexity in D to something that has exponential complexity in D. And that means we're going to have to be a lot more clever about how we approach the problem. But there's going to be a lot that's in common. Overall, we want to use cross-validation to select among our different models, just like we did before. But again, the key thing will be managing computational complexity. So that's what we're going to do, starting with Unit 4. Okay. And we're going to learn some nice additional things like maximum likelihood as a sort of generic statistical approach to training machine learning models. Okay, so let's start with our data set, the data set that's we're going to focus on for our demo. So it has to do with PSA testing. So PSA is used as an indicator of prostate cancer. So basically, it's something that you can pretty easily measure in the bloodstream, and by measuring the amount of it, if it's really high, that's a likely indicator of prostate cancer. So there's a famous study from 1989 where they measured the PSA level of 97 men. They also measured 8 different biometrics, like I think all these men had cancer, or maybe a large number, so they measured the cancer volume, the prostate weight, their age, various other things. So that gives us a nice data set that has 97 samples and 8 features. And the target will be PSA, or almost PSA. The thing about PSA is it really can span many orders of magnitude. So rather than working with PSA directly, we want to look at or try to predict the log PSA. So that's going to be a lot easier. So, so these are the different features. As you can see, a lot of them probably only make sense if you are in the medical field. But basically, this data set, you can find this on the web. It's something that is used in this Elements of Statistical Learning, which is a really famous textbook for machine learning. So let's try to work with this data. So the first thing we might try to do, since we know how to do it, is to use multiple linear regression. So as we know, y hat would be beta 0, plus beta 1 x1 all the way down to beta d xd, where in this case we have d features and y is the log PSA. And so you might ask, okay, why are we doing linear regression? So one of the reasons we've talked about before is because it's pretty easy to do. We know how to do it with least squares, all that. But there's actually another reason that we haven't really thought about until now, which is that sometimes when you do these model fits, you're actually interested in learning about the underlying physics or the underlying biology or something. And so if we do this model fitting of this model, and we find that a certain one of these is very large relative to the others, a certain beta, large in absolute value, that could give us an indication that that is actually more predictive of the targets than some of these other things. So this is actually used quite a bit when people do science. They're trying to learn about the real world, and so they collect a bunch of data, and they do a linear regression, and they look at the size of the parameters, and they say, oh, okay, this one parameter is really dominating the rest, so that's probably explaining the data. That x explains this y, or maybe a subset of x's. Okay, so that's kind of a key point for this model is not only is linear regression something that is easy to formulate, but it's actually interpretable. There's many other kinds of regression that are, maybe they work better, but you get a model that's difficult to understand or really explain, or get some interpretation out of. Okay, there is sort of one little catch there. We have to be careful when we compare the size of the betas if we really want to rank the different importance of features. We have to make sure that the different features themselves have roughly the same size, right? Because it could be that one of these features in the data is just really tiny, so in order to use it at all, you need to make beta super large, but that doesn't necessarily mean that it's important. It might just mean that that feature was scaled really small. So to really make sense of whether the larger beta hat means that variable has larger importance, we need to make sure that the features are roughly the same size. And we'll do that by normalizing our data, and we'll talk about that in just a few slides. Okay, but otherwise, this is stuff we've seen before. We can use the linear model dot linear regression. There's a reason why we're going to turn the intercept off. We'll talk about that in a moment. But and there's also some shortcuts. There's a lot of shortcuts in scikit-learn that we'll kind of learn as we go through the semester, but we'll usually start out by doing some approach that is very manual just to understand it and takes a lot of coding, but then later we'll realize that there's actually like a one-liner in sklearn. So for example, if you want to compute something like the mean squared error or the RSS, you can do that in one line with sklearn, for example, using this cross-val score. So we're computing the cross-validation mean squared error. You just give it the estimator, which is our linear regression object here. You give it your training x, your training y, and so actually this is going to be our full data set of x and y, and we're going to use, now you tell it what kind of cross-validation. We're going to use something called repeated k-fold, which is like the k-fold that we learned about, but it does it several times with different random seeds to try to make it less dependent, more consistent. And you can also tell it exactly what to report. It's going to report some sort of score that the larger it is, the better the fit. And so negative mean squared error makes sense. You could also have it return RSS or many other different things. But we're just going to do negative mean squared error, and we find that we get this value of 0.404. So the question is, okay, is that as good as we can do, or can we do better somehow, perhaps by leaving out a subset of the features and focusing on the ones that are more important? And last time in the last unit, we learned why that is. It's because for a fixed data size, the more complex your model is, the larger the variance term in the bias variance decomposition of MSE, right? And then the worse your performance gets. So it's this sort of, again, it's a model order selection sort of thing. If we select too few coefficients, we're going to have bias problems. If we select too many, we're going to have variance problems. We want to find just the right subset that does the best job modeling our data. Of course, no one tells us what that subset is, so we have to learn it ourselves from the data, and that's the challenge we try to face in this unit. All right, any questions so far? Yeah.
What is the fifth underscore intersection?
Oh, yeah. So when you fit this model, you can tell it to force the beta 0 term to 0. And it doesn't make sense why we're doing that right now, but it will make sense in a few slides. Okay. All right. Any other questions? Yeah.
Is there a reason we're saying the scoring equal to negative mean squared error instead of just the mean squared error?
Yeah, because the score for cross-val score, it's built such that higher scores are better. And with mean squared error, lower is better.
Okay.
So to be consistent, they have to put the negative. And now negative mean squared error, right, higher is going to be better.
Right. Okay.
So yeah, it's just because all their scores work that way and they're trying to be consistent. Okay, good. Any other questions? All right, so let's talk about feature selection. So as we just said, from last lecture we learned if you have too many features, D being too high, that implies a large error variance, which you could say implies high MSE or RSS. Okay, so we want to use fewer features. In fact, we want to use as few features as possible as long as we can model the underlying structure of our data well. So the question is, which features do we use? So, and again, feature selection is the problem that we're facing now, which is we want to select the best subset of D total features. Okay, so the very first approach that you can imagine doing, which is feasible if you have relatively few features, is exhaustive search. That means you try every one of those 2 to the power D subsets. So this is every possible subset. And what you do when you try it is you run k-fold CV or some kind of cross-validation for every one of those choices. And when D is small, this is feasible, but when D is large, it's impossible. In any case, this is the optimal approach to feature selection. So if you really want to know what is the very best approach, it is this. It's just that you can't always implement it. Okay, so as a result, we're going to now talk about more practical approaches. First, we'll talk about stepwise selection, then correlation-based methods, and we'll spend the majority of this unit on regularization-based methods like lasso. Okay, any questions on the exhaustive search before we move on? Okay, so that's going to be the gold standard. At the end, when we do the demo, we'll show like how all these other methods compare to exhaustive search, and we'll see that at least for this data set, we can get close to exhaustive search performance, but not quite there. Okay. All right, so the first approach is known as stepwise selection or sometimes stepwise regression. And this is basically, you could say it's a greedy approach. And it goes like this. There's sort of 2 ways to do it. There's the forward selection and the backwards elimination. So let's talk about forward selection first. So what you do is you first look through all your features one at a time. And you measure the cross-validation RSS or MSE for each one individually. Whichever one is the best, the lowest RSS, you keep that one. You add it to your list of these are the features I'm going to use. Then you look through the remaining D-1 features and you select each one at a time and you combine it with the first one you chose. And now you're looking at pairs of features. But again, you have only D-1 options in this case, right? Once you find the best one, you add it to the set of features you're going to keep, and now you have 2 features. Now you look at the remaining D-2 features, and you select the best one that works in conjunction with the 2 that you already saved. And so now, once you figure out the best one, now you have your 3 features, and so on. So you keep doing this, adding one feature at a time until you find that, so originally, when you start to do this, you should probably see the RSS starting to decrease as you add more features. Well, eventually, the cross-validation RSS will start to go up, right? Because now your variance is worse than your bias. as you add more features, your bias should be going down, but as you add more features, your variance goes up. At some point, the variance overwhelms the bias, and now you have too many. That could be a good place to stop. Or sometimes you have a computational constraint that just says, I can use at most 10 or whatever it is, and so you might stop even before then. Okay, so that's forward selection. Is that making sense, what we do? Okay, any questions on that? Okay, we can also do backwards elimination, which you start with the list of all your D features, and you look at the RSS computed using cross-validation for that, and then you remove one at a time. And you find the best one to remove, and now you save that new list. Now it's D minus 1. You remove one at a time again, figure out which is the best one to remove, and so on. And this way, your list of kept features will be getting shorter and shorter. Your mean squared error, or RSS, should be getting better and better up until some point when bias overwhelms variance, and then it starts to get worse. So at that point, you stop, or maybe you stop even before that if you have some minimum allowed number of features. So there's different ways to parameterize this. But you can see that it's similar to forward selection. It's just you start with the full set and you gradually remove features one at a time. So those are the two approaches. Neither of them are optimal because you're only looking ahead one step. And so as you guys know, in life, generally speaking, you want to have a long-term view when you make decisions or allocate resources. If you just think like 1 day ahead or 1 hour ahead or 1 minute ahead, that's not always the best decision-making process, right? And that's the case here. You're just looking at one feature at a time. What should I remove now? Well, it could be that if you remove this feature now, then that's going to cause problems later. You actually should have kept that, but it wasn't evident when you removed it. So that's something that, like the optimal approach, which considers every possibility, it doesn't fall into that trap. So these are greedy, or otherwise known as myopic. They only look one step ahead. But still, in practice, they actually do work pretty well. And in scikit-learn, they're implemented in RFE-CV. So that's recursive feature elimination using CV. Okay, so it's implemented for you there. All right, so any questions on this approach? Okay. So there's another approach. This is, again, a heuristic approach, suboptimal. And the idea, maybe the first way to describe the idea, is that you want to choose the features which are most correlated with your target. Because you remember, like when we were studying univariate feature selection or simple regression, when we were studying simple regression, remember what the relationship between r squared and one of our statistical parameters, do you remember what that was? R squared was equal to?
Rho xy?
Yeah, rho xy squared, I think it was. So like the higher rho xy was, the higher r squared is. So there it suggests, oh, we actually want that our features are correlated with our target. So when you have multiple features, though, it's not so simple. But this is still the idea on which this approach is based. So it kind of goes like this. You first imagine you're only going to use one feature, and you go through your different features one at a time, and you look for which ones have the highest sample cross-correlation or cross-covariance. So this is, if you normalize this, that would be the rho, but this is the unnormalized version. And so you just look through them one at a time, and you find the single one that's most correlated. Then you can say, okay, that's what I could do with one feature. I would just choose the one that's most correlated. Now, if I had two features, you could maybe rank the correlations of all the different features and choose maybe the 2 that are most correlated, or the 3 that are most correlated, or the 4 that are most correlated. So essentially, once you compute these correlations or covariances, you can just use model order selection to figure out, do I just use the single most correlated, or the 2 most correlated, or the 3 most correlated, right? So you reduce it to a model order selection problem that has complexity order D, and that's feasible. So that's the general approach. So use cross-validation to optimize the model order P. So basically find the P features most correlated with the target for different P, and then use cross-validation to optimize P. Okay, is the idea clear enough? Any questions on the idea? Okay, so this sometimes works okay, but not always, because, well, here's one way to see why it might not work so well. Imagine that you have two features. They're both highly correlated with the target, but they're also highly correlated with each other. Let's take the extreme case where two of your features are just identical to each other. There's some sort of repetition in your data set. And maybe that identical feature is the one that's most correlated with the target. Well, if you use the two of them, obviously that doesn't give you any benefit over using just one alone, right? It's totally redundant. But still, this method would say you should use both. So you can see that maybe this idea is a bit heuristic. It's not complete. And there are versions of this idea that are more sophisticated, where in addition to rewarding correlation between features and target, you also penalize cross correlations among your features to try to get rid of that problem. But again, it's not exactly clear how to do that. And so it's just sort of a heuristic family of techniques. Okay, so is that part pretty clear? Okay, and correlation is not the only thing you could try to maximize. There's other statistics like mutual information or F value or P value, and if you don't know what those are, it's not a problem. They're just things that are similar to correlation in spirit, but defined in a different way. They're things that you could imagine you would want to have a high mutual information, let's say, between your features and targets. And so these are all options that sklearn gives you. It says you can use correlation, you can use any of these guys in this function select k-best. So you sort of tell it which is the univariate statistic. That means like correlation is one choice, or these other guys. You just tell it which one you want to use, and it basically ranks them, and here's the best to the worst, and then you have a model order selection problem. Yeah, so this is just another option, something that people do once in a while, but I find it doesn't work super well, but it's something good to know about. Okay, any questions on this approach? Okay, all right, and then we'll get to our last approach now, which is regularization. This is the one, like I said, we're going to be spending most of our time studying. So, all right, so let's kind of get into the idea. So back in Unit 2, we said the way we're going to train our model is we're going to define this RSS cost as a function of our model parameters beta, and then we're going to find the beta hat that minimizes that cost on the training data, right? That's what we do. But as we saw, that if you actually use training RSS as a guideline for model order selection, it always misleads you. It always tells you to choose the most complicated model, because the RSS just goes down and down and down as the model gets more complex. So that's a flawed idea, but what if we add some extra thing to our optimization? So it's not just training RSS, but some other penalty, and this is what we call regularization, or sometimes people call it a penalty term. And that thing is going to penalize us from choosing too many features. So it kind of goes like this. If you imagine asking the question, should I use this jth feature or not? Imagine putting it in your model or taking it out of your model. When you put it in your model, you know that this should go down because your model got more capable, and so yes, you can get a better least squares fit, but you're going to build this penalty so that actually this is going to go up. So basically, in order to justify putting that jth coefficient in your model, you have to get a bigger decrease in RSS than you do an increase in this penalty. So that's basically how it works. Of course, we have to talk specifically about how we're going to build these penalties, but that's sort of the idea, is the training RSS must decrease more than the penalty increases. So if you see a huge boost to training RSS, that's a sign that, oh yeah, maybe that is an important feature. But it's going to have to be so good that it overwhelms the penalty for adding that feature. So that's essentially the idea. Is that making sense? Okay, so let's talk a little bit more detail about how we can build some of these penalties. So again, when we talk about RSS and minimizing, this is how we did our model training back in Unit 2. RSS has this form. We have our training labels and our predicted training labels or targets as a function of the beta that we're designing. So the goal is to modify this to do feature selection as well. And we said that the idea is to penalize the use of these features. So we're going to add this extra term that goes up as we include more features in our model. So overall, if you turn your features, if you decide not to use a feature, that's equivalent to setting beta j equals 0, right? Because you multiply it by 0 and then it's not essentially used at all in your model. So this penalty or regularization term is going to be minimal when beta j equals 0, but when beta j is not 0, it's going to start to grow. The larger beta j is, maybe the larger that penalty gets. So that's the idea. And the question now is, how do we choose that penalty function? Okay, so here's the two that we're going to focus on. Let me make sure I get the notation. Okay, so we're going to look at L2 regularization, which is going to be alpha times the sum j goes from 1 to d of beta j. I'll just write beta j squared. And then L1 regularization is going to be alpha times the sum j equals 1 to d of the absolute value of beta j. So one of them is squaring beta, the other is absolute value of beta. So as we'll learn, these two different penalties have a very different effect on our overall design. So the first way we can try to understand what's going on is just to make a plot of the penalty term for a specific j. So here we have our quadratic, or familiar quadratic, and then here we have our absolute value, right, as a function of beta. So when beta goes positive or negative, in both cases, the penalties increase, but they increase in different ways. So what you can notice about the quadratic term, well, yeah, what could you, if you wanted to describe things qualitatively, how could you distinguish these two? How are they different in words? Yeah.
The quadratic term will go faster while the other one is linear.
Yeah, there's kind of two ways to look at it. You can say for large beta j, the quadratic term is bigger. What about for small beta j? It's the opposite, right? For small beta j, quadratic term doesn't really care that much, but the absolute value term really does care if beta j is different from 0. Quadratic term, like as long as beta j is sort of in the neighborhood around 0, it's more or less, it's very small. Whereas the absolute value term, it doesn't get to 0 unless you really set beta j to 0. Okay. And then both of them have this weighting term, alpha. And alpha is an adjustable parameter. It's going to be a non-negative number that we choose. It's going to be a hyperparameter, something that's going to sort of control the model, the complexity of our model. And it's going to be something we choose based on cross-validation. Okay, so the larger that alpha is, the stronger the penalty is, the more it really wants to force all our beta coefficients to 0. And if we set alpha really small, or in fact all the way to 0, then it's like the same as taking this out of our formulation. Okay. Another comment is we are not penalizing the intercept term, beta 0. So that generally speaking, we want that to be on. It's really just trying to sort of do sort of a calibration. It's not something that we think of as a bias variance trade-off type parameter. So that term, as you can see, it's not involved here. The sum started j equals 0, sorry, j equals 1, not j equals 0. Yeah.
Why are you penalizing a higher value of beta j? Like, a higher value of beta j doesn't imply that you're adding on more beta like values, right? Which just means
Yeah.
like in fact that it implies like a higher dependence on that variable. So why would you want to penalize that?
It's a great observation, and I'll answer your question in a moment.
Alright.
But yeah, there actually are other costs you can imagine doing. Like one of them is kind of like this, where it really says like when beta j is near 0, that's really good. And then if it's different from 0, well, it doesn't matter how big or small it is. It's just different from 0. It's kind of like you might say like there's this optimal thing like this that you'd like to use. Turns out that both of these guys give us what are called convex optimization problems that we will eventually have to solve to choose our betas, and we can solve them in a guaranteed way. Some of the other fancier penalties, like things like this, give us non-convex optimization problems that are difficult to solve. And so even though you can do that and sometimes it works well in practice, it might be difficult to know whether your model is actually minimizing this cost that you set up. So that's kind of why one of the reasons why we're focusing on these two choices. Also, these are the two most common choices. So, but yes, it is good to point out that there are other options here, and we will see exactly the problem that you're noting, that this is actually penalizing the size of the betas as well as whether they're 0 or non-zero. Yeah, great observation. Okay, and we'll have a remedy for that too. Yeah.
This way we are like assessing the performance of beta in collection and penalizing them. Why don't we penalize each beta by itself, like individually? Wouldn't it be better to know how each beta is performing as a sum?
Well, in some sense, like I don't know, if I expand that square, then I just have a sum of terms, each one on its own, right? So I don't. How are you suggesting to do it differently?
We have a single f for the whole sum. We don't have like a penalizing term for every beta to penalize each beta differently.
Oh, you mean like a different one of these?
Yeah, for every beta, like for every beta j.
It's a lot of tuning parameters. So then it's not clear how to choose all those tuning parameters. Yeah, it's a possibility. It just gets complicated and might lead to more complications than benefits. Yeah, but as we'll see in a moment, the key to using a penalty of this form will be to make sure that all your features are scaled to approximately the same size. And once they are, then you can sort of trust them equally, and then something like this makes sense. But yeah, we'll talk about that in just a moment. In fact, this slide. Okay, so here's the point. We have to standardize our data. So standardization is sort of a term for a fancy kind of normalization. And so I'll describe it now. So as we just talked about, these two regularizers, they penalize all the beta j coefficients uniformly. Like, beta 1 and beta 2 and beta 3, they're all treated the same way. So that's going to be a problem if some of our features are very much larger than others, because then essentially the large x's, it seems like we would want the beta j's to be small if x is large to balance things out, but now with this kind of penalty, it doesn't acknowledge that. So what we're going to do is we're going to normalize the xj's. In particular, we want to set them as follows. We want to set them so that their average squared value for each j, okay, this is for all j, their average squared value is some number like 1. We just choose 1 because it's convenient. This is basically calibrating their average squared sizes. And as we know, the average squared size is nothing more than the sample mean squared plus the sample variance of that feature. So it's like we want the sum of these two to be 1 for all of our features. To make that a little bit easier, what we do is we also remove the mean of the targets and of each feature. And so if I remove the mean of each feature, then this automatically goes to 0, and really I'm just scaling what remains so that the variance equals 1. Okay, so this is basically standardization is two things. It's removing the mean of the target and all the features, and then for the mean normalized, or the mean removed features, you scale them so that they all have a variance of 1. So this is a very common thing to do with your data as soon as you get it. You just standardize it, and yes, question?
Is removing the mean just like offsetting all the data so the mean is equal to 0?
Yeah, essentially, I mean, yeah, if you remove all the means from the features and the targets, if you think about back to the equations from Unit 2, that tells you that beta hat 0 should be 0. The intercept term can just then be set to 0. And that's why we saw it set to 0 back here at the beginning, because in the demo, before this line, we normalized or standardized our data, set the mean to 0, so now it's appropriate to tell our model, don't worry about fitting the intercept because it's going to come out to 0. We know that. Okay. So that's the motivation. The specifics goes like this. Imagine that these are your original features. You compute the sample mean of each j. You subtract that from all of the xij's. And then you divide the result of that by the standard deviation of xj. And then you basically take the result and you call that xij again. You just rename it. And here we're doing the same exact thing to the y's. And there's a way to do this in sklearn using this standard scalar object. So here we instantiate it. And then in this line, we're doing fit transform, which does two things. The fit part of it computes these things, and the transform part of it applies them in this way to normalize our features. So this is our original raw data, and out comes the data we're going to use for training our model. And then here we're doing something similar with the labels. We just have to do this little fancy reshaping here because this function wants this to be a matrix-shaped, not a vector-shaped quantity. So what we're doing is we're just temporarily saying, okay, let's add an extra dimension onto here, and then we can run this, and then we can take that dimension away, and now it's back to the vector that it was. So this is like vector to matrix and back. Okay, so this is what we do with our training data. And then, this is a very important point, when you have your test data, you want to use the same procedure, but you need to use the training statistics, not the test statistics. So it's not like you go and apply this same procedure to your test data. The fit part you don't want to do. There's sort of two ways to think about why you don't want to do that. The first way is you can think of this standardization as the first in a chain of processing steps that goes from raw data to prediction. And once you train that chain of processing steps, you want to make sure that's the same set of steps that you apply for training and test. Otherwise, you're going to be a mismatch, and it probably won't work well. Okay, the second way to think about it is quantities like this are easy to estimate when you have lots of data and difficult to estimate when you don't have much data. And for example, when we do our test prediction, maybe we just have a single test sample, just one sample. It's impossible to estimate the standard deviation from one sample, right? So we can't even compute these test quantities in general. But that's okay because we're not going to use test quantities. We're going to use the training statistics when we standardize the test data. And if you don't do this, you'll see that it just basically doesn't work. Okay, but this is a common thing that students miss, so I want to emphasize it. Yeah.
If you use the training statistics, will the test data that's standardized still have the sample mean of 0 and the variance of 1?
No. But it's not important that it does. Yeah. Okay.
Why do you have to use the training statistics and not the test statistics again?
There's kind of two ways to think about it. One way is that if I think about this standardization as the first in a sequence of manipulations of my data, I want that sequence of manipulations to be the same for training and test, because I'm like going to spend a lot of time getting that chain of commands well designed, and then if I change it when I actually apply it in practice, that's a big red flag, right? Maybe I've broken it. Secondly, you can't necessarily estimate these statistics well on the test data when the test data is very small, like one sample. So even if you tried, you wouldn't be able to do it with one sample. Question? Similar?
Why don't we have to worry about the scaling for testing?
Well, why are we doing this?
No, what you said, like, we shouldn't just told them that we shouldn't worry about scaling of test data. It should only be done on the training data.
Oh, you do have to do it. You have to standardize your test data. It's just that when you do it, these things are calculated on the training data, not the test data. Yeah, if you don't standardize it, you're going to have terrible mismatch. It's going to work. It's not going to work at all.
Why don't we use both?
Well, because the test data is something we're not allowed to use for design, right? It's this thing that we won't see until we're done designing. Okay, great. So everybody good on standardization? Okay. All right, so so now let's come back to putting together the regularizations that we have proposed, which is the so-called L2 regularization and L1 regularization, together with RSS. That's what we learned to do back in Unit 2. So now we're saying let's actually minimize the sum of these. So previously we saw that RSS could be written in terms of this Euclidean norm like this, and it should be evident that this is also the squared Euclidean norm of our beta vector, but this is kind of an important little point, is that here, when we define the beta vector, there is no beta 0 in it, right? Usually the beta 0, I put that in the beta vector, but now it's left out, and the reason we can leave it out is because we're going to assume that our data has been standardized, so we know it should be 0. Yeah, so that's, and it's important because if I had the beta 0 in there, that would be bad because we don't actually want to penalize that term. We want to leave that free to fit the data as it wants to. Okay, so what we have now is when we train our model with this approach, this is called ridge regression. We have the RSS, like always, plus alpha times the Euclidean norm on our parameter vector beta. And so as it was pointed out, the effect of this is going to say, yes, fit your training data, but also make sure that your parameters beta are not too big. It's just going to penalize their size. It's going to say shrink them towards the origin. So that's one option. The other option is we take RSS and we add it to this over here. Now this, when you see the little subscript 1, this refers to the so-called L1 norm. And then this one is when you don't see any norm denoted, that means use the standard norm for that type of object. And for vectors, for real valued vectors of finite dimension, the standard thing to do is to use the Euclidean norm. And if you want to notate it explicitly, you put a little subscript 2 there instead of nothing. Okay, so the point that I want to make now is that both of these guys are norms. They're just different ways of thinking about a norm. A norm is a way of measuring length or distance between two places. And we're all very familiar with Euclidean distance, right? It's just like, it's the straight line between 2 points. So if you're in New York City and you're a taxi cab driver and you're at one point, you have to pick up someone at another point, and you want to measure the distance from you to your pickup location, you can't use the same distance that a crow would use to fly there. You have to say, well, I'm actually going to go down this street, and then I'm going to turn on that street, and that's going to be my distance. That is actually what the L1 norm is minimizing, right? It's minimizing the absolute value of each one of those separately. So let me draw a little picture. So if I have 2 points, the L2 norm is the distance from there to there, whereas the L1 norm is the sum of this and this distance. It's just another way of measuring distance, but it still satisfies all the mathematical properties that you need for a valid distance, or basically valid norm. Okay, so sometimes this L1 is called the taxi cab norm. Okay, but as we'll see, there's a much more important difference between how these things react when we start to use this for linear regression. Oh yeah, and by the way, this last thing is called lasso. It stands for the least absolute scaling and shrinkage operator, but everyone just calls it lasso. Okay, everybody good with these definitions? Right, so let's look at ridge regression a little bit more closely. So this is the way we define it. It's RSS plus this scaled sum of squared terms. And it turns out that because this whole cost is still quadratic, you can do a derivation very similar to the derivation we did in Unit 2, and you can derive in closed form that the minimizers of this, in other words, beta ridge, is given by this expression, which still involves a matrix inverse, something like A transpose A, but it's slightly different. So one of the important things is we don't have the A matrix anymore, because remember, the reason the A matrix, it had that first column of ones that multiplied the first coefficient of beta when that coefficient was beta 0. We've taken out the beta 0, so now we take out the column of ones, and we're just left with the raw feature matrix, or standardized feature matrix X. Okay, so that's what we have instead of A. And then you see that there's this part here. This is really the effective alpha. So when alpha goes to 0, not surprisingly, this looks just like your least squares design that we derive. But when alpha is non-zero, then it has the effect of making this term that you're inverting a little bit bigger, which makes the inverse a little bit smaller, and it means that this is shrunk towards the origin. Okay, so why would one use this penalty? Why use this L2 penalty? So it turns out that the main reason that you want to use it in practice is not for feature selection, as we'll see. It has to do when the columns of your data, when your different features are very correlated. So let me try to illustrate this a little bit. So if you remember, we saw some pictures back in Unit 2 that looked like this. So we had maybe beta 1 and let's just say beta 1 and beta 0. And these are the RSS contours. And this would tell us that the optimal design, the one that minimizes RSS, would be at the minimum. So these are like equal cost contours. It's like a topographic map. Imagine that there's some bowl-shaped thing curving up whose minimum is here. Right? So it turns out that when your features get more and more correlated, this bowl gets more and more stretched. And in fact, the center itself may move. The center may move very far out from the origin. The bowl can get extremely stretched. And so it turns out that the solution, the minimum, can land very far from the origin. In other words, you can get huge beta values when you have high correlation. Because maybe what your beta values are trying to do is they're trying to decorrelate your features. And if they're highly correlated, it's like it has to do this crazy inverse with really large numbers. And once you have those really large betas and you apply them to test data, you can get overfitting. Basically, they're very sensitive to the values of the test data and things can go crazy. So basically, feature correlation can make this cost surface. That's what I'm plotting here. It can make this very stretched out, and it can make the minimum beta very far from the origin. And that large beta least squares means that the test predictions will be very sensitive to the test features. In other words, overfitting will happen. And so by penalizing beta, we move the solution towards the origin. We actually change the shape of this because what we're doing is we're adding, where do we have it? Oh, sorry. Because we're adding this component here, it's going to bring the solution closer to the origin, and it's going to reduce overfitting. And we'll actually see in one of the labs coming up, I think it might be the lab for this Unit 4, where you have really super correlated data that this is really helpful to get better performance. Okay, so this is the main reason people use ridge regression, is to deal with correlation, not feature selection. So it is an important technique. Here's another way to see why you might not want to use it for feature selection. So this is a nice plot. It's called the coefficient path. And it shows what happens as your alpha parameter gets large. So intuitively, when alpha is very small, you just have the least squares solution. As alpha gets larger and larger and larger, you have a stronger and stronger penalty. And eventually, you really just care about making this term, making this small. Once alpha is super large, maybe this completely overwhelms this, so this doesn't really matter, and it just says, set your betas to 0. And that's what you see over here. So when alpha gets really large, like 10 to the power 4, you can see these are all the different alpha coefficients, sorry, all the beta coefficients. You can see they're all getting pushed to 0. So over here on the left side, you have the least squares solution. And on the right side, this goes basically to the 0 vector. And in the middle, you can see what happens is you're squeezing all those coefficients towards the origin. But there's interesting things happening. It's not like they're just all scaling together. You can see over here that they're actually changing orders, right? So there is something interesting happening, and that interesting stuff can actually help with correlation. Okay. All right, so that's ridge regression. Do you guys have questions about ridge regression? Okay, so, and as always, how do you choose alpha? You choose it with cross-validation. So k-fold cross-validation, or you have some test set different from your training. But you want to find the alpha that minimizes your some criteria like RSS or MSE. And in this particular plot, this vertical line shows the alphas that minimize the test RSS for this data set. It was that particular alpha. Okay. All right, any questions on ridge? Okay, so very quickly, lasso, as we know, it's similar, except it has, instead of the 2 norm, square 2 norm, it has 1 norm. So there's a few things that change now. This problem is no longer as simple as the last one. We cannot derive a solution on paper. However, it is something we can minimize numerically because it's a convex optimization problem. And we will talk about this, what that means in Unit 6. But for now, it's enough to know that the solution is easily computable. There's many fast numeric solvers to do this. And there's implementations in sklearn, so it makes our life easy. We don't even have to tell it which solver to use. But the main question now is, why would we want to use this penalty over the other one? So what's interesting now is that this penalty, unlike the L2 penalty, leads to exactly 0 betas, which means it actually does feature selection. And by controlling alpha, it controls the number of non-zero features that you have. So here's the coefficient path for lasso. So again, way to the left side, you have the least square solution. As alpha gets larger and larger, you eventually go to the 0 solution. But in between, there's interesting things that happen. But the key thing to notice is that these featured values, their amplitudes, they get shut down to 0. Right? So like, if you look at what's happening in this region of alpha, there's only one non-zero feature, and it turns out to be this LCA volume. If I adjust my alpha a little bit lower, now there's two features. These two. And so you could say, well, this LCA volume is probably the single most important feature in your data set, at least according to Lasso. Second most important would be the purple one. Third most important would be the orange one, and so on. So it does suggest which features are most informative. It does set the features exactly to 0. Any questions so far? Almost done. There still is a problem, though. As you can see, it shrinks the values of those features towards 0. So for example, when I'm in this range of alphas, yes, there's only one feature that's still standing, but as I move alpha from here to here, the size of that feature plummets towards 0. As you can imagine, the prediction is going to change drastically as you go from here to here. So the solution to that is what you use Lasso for is not to get these amplitudes. It's only to figure out which subset of features is non-zero. And once you know that subset, like maybe you do cross-validation, you figure out I want to choose this alpha. Now you say, okay, there's 3 features left. I'm going to take those 3 features and I'm going to go back to least squares regression with those 3 features. There's no bias there. There's no shrinkage towards the origin. So you're kind of separating, you're using Lasso for selecting features, but not for actually computing the beta values. So that's the key message. We'll talk about that more next time. We're out of time today. But that's essentially how we're going to use Lasso, and we'll see that leads to a little bit of a complication, but several strategies for choosing alpha. Okay, so see you guys on Wednesday.